So, hi everyone. We're happy to have Sam Spiro here to talk about slow Fibonacci walks.
Do I have access to screen sharing, Alex?
Oh, you might not. Let me make sure. I might have forgotten to add you to a host. Yes, you are now a co-host.
It's much easier. Okay, yeah, so thank you all for coming. So I'm talking about slow Fibonacci walks, and the first half of this whole talk will be joint work with Fan Chung and Ron Graham. I know that the two organizers for this seminar and a lot of the past talks have been kind of on the algebraic side of things, which isn't typically what I do, but I figured a good way to start us off would be with a question from Richard Stanley, but probably one that most of you aren't very familiar with. And it's the following question, which is him asking Math Stack Exchange for magic tricks involving deep mathematics. And the example he gives is the following. So you're a magician and you ask an audience member, Alice, to choose an integer between 1 and 50. And then given these two numbers, you add them, get a third number. You then take the largest of these two numbers, add them to get a fourth number, and so on and so forth. And you just keep repeating this process about 10 times. And eventually she tells you, she does this process without telling you the first two numbers, then she tells you her final number is n. And then you as the magician say, oh, if you did this one more time, you would get roughly the golden ratio times n as your number. And then she does the computation, then she's amazed, and everyone's amazed, and it's very exciting. And the intuition with why this works is that roughly the sequence you have follows a Fibonacci-like recurrence relation, just adding the previous two terms. So after enough steps, roughly your next term should be like the golden ratio times the previous one. So if you actually go and compute some things for this, it turns out not to be quite true. It's roughly correct that this happens, but it's not entirely the case. So a couple of years ago, I believe Richard asked Ron Graham for kind of a related process and saying when you can say it is, the next step of this process is the golden ratio times n. So kind of with this as background, we'll define our relevant object, which is Fibonacci walks. So what we'll do is, like Alice, we'll start with two positive integers a1, a2, and we'll define the a1, a2 Fibonacci walk to be the sequence which starts a1, then a2, and then follows the Fibonacci recurrence for the rest of the term. So for example, if we take the 10-2 Fibonacci walk, this is the sequence that goes 10, then 2, then 12, then 14, and so on and so forth. And we'll say that Fibonacci walk is an n Fibonacci walk if it eventually hits the number n for some s. And for example, this is a 40 Fibonacci walk because it eventually hits the number 40. And the first question you might have about these walks is whether there exists an n Fibonacci walk for all n. If you think about it for a bit, you'll come up with the answer is yes, for a dumb reason. Namely, you can always take the walk that starts 42, n, so on and so forth, and that will hit the number n, whatever n you're thinking of. But that's kind of boring, and also if we want to study what happens in the next step of the walk, we definitely have no control over this very general setting. So to make things a bit more interesting and to give us a bit more control, we'll look at slow Fibonacci walks. And these are walks that hit n eventually, but would hit it as slowly as possible. So for example, here are 4 different 40 Fibonacci walks. This first one being kind of one of these sum ones where you can start with anything and then 40 and you hit it. But these first 2 walks aren't slow because this one hits it in 2 steps, this one hits 40 in 5 steps. But as you can see, there exist Fibonacci walks that hit 40 in 6 steps. And in fact, if you go into a computer and test things, you'll see that these are the 2 unique 40 slow walks. And this is me just saying these things. And so these are the objects we want to look at, the things that hit 40 in like the least trivial way possible, as slowly as possible. So we want to study these slow Fibonacci walks And it's basically equivalent to study the initial pairs BA that generate the walks. And we'll call such a pair good if its corresponding walk is slow. And you might notice that this BA notation is kind of unnatural, but it'll end up making our final theorem statement a little cleaner, which is why we do that here. So again, understanding these pairs is equivalent to understanding these walks. So what structurally can we say about these good pairs? So the first observation you might make, you first would define S of n to be the length of some n slow walk. And then your first observation is that if you look at the number 1, the only slow walks you have, all the slow walks you have are of the form x comma 1, where x is whatever number you want. And for every other n, you can find a longer walk that takes at least 3 steps. And then this proves pretty quick. If you claimed you had some slow walk for 1 that took at least 3 steps, say starting with xy, then your third term would be x plus y, which are both positive integers, which is at least 2, so that's impossible. And for any other n, you can start with the positive integers 1 and n minus 1, and then on the third step, you'll get to n. So what this lemma says is that for 1 slow walks, we really can't say much about the structure of the Fibonacci walks. So hopefully, for larger n, we'll be able to say something more. And it turns out this is going to be the case. So another quick observation one can make is that if your length of the slowest walk is larger than 2, in other words, if you're not 1 by the previous lemma, then if you have a good pair, it must be that A is at most B. And the proof of this is by example. So if someone comes up to you on the street and says, hey, I have this slow Fibonacci walk for 1014, and this generates some number n as slowly as possible, you should be concerned for 2 reasons. The first is this random man is not practicing social distancing. And the second reason is that he's wrong. Namely, I don't know what n he's thinking of that's generated as slowly as possible by this, but a slower walk will be the one that starts 6, 4, 10, 14, and so on and so forth, because this sequence generates everything that this sequence does as well, but 1 step slower. So we know that whenever we have a good pair, it has to have this property here. So another observation that's easy to prove, but perhaps not obvious from the get-go, is that if you look at the case step of any walk BA, it'll look like this linear combination of your initial terms times some Fibonacci numbers. And this is pretty easy to prove by induction on K. And this lets us say a couple things. So in particular, we have the following, which says, if we have an n good pair BA, if we already know 1 good solution, then all the other good solutions, B prime, A prime, are of the form A plus some multiple of the S minus second Fibonacci number, and B minus the same multiple of the S minus first Fibonacci number. And we need both these to be positive as well. So as an example of this, if you believe me from earlier slides ago that the slowest walk to hit 40 takes 6 steps, and that 10-2 is a 40 good pair, then what this lemma says is that all the good pairs are of the form 10 minus 5k and 2 plus 3k. And if you take k equals 0, you just get back 10-2 again. If you take k equals 1, you get 5 comma 5 as the pair, and no other value of k gives you 2 positive integers. So this says that the 2 unique good pairs are guys we said before. So with this lemma, all we need is 1 solution, and then we know everything else. And well, to prove this, we just use the previous lemma. So say we had so n good pair B prime A prime. Well, by definition of being n good, that means on its S step of its Fibonacci walk, it hits the number n. But also by this lemma, we can expand this as this sum of Fibonacci numbers. So now A prime B prime is just a solution to this linear Diophantine equation. And we already know a particular solution, which is AB, or BA technically. So they just have to be related in exactly this way. So these are all some pretty basic observations you can make after staring at the data for long enough. And with this, we can prove kind of our main technical lemma / theorem, which I'll often refer to as the characterization theorem, which is the following. So given some n bigger than 1, and s the length of its slowest walk, there exist unique integers a and b, such that one, n can be written as this special linear combination of Fibonacci numbers, and two, they lie in this range. A is at most b, and b is at most the s minus first Fibonacci number. And moreover, in this case, BA is an n-good pair, and by the lemma we had before, that means we know the structure of all the n-good pairs. So let me briefly prove this based on what we already know. So again, by this previous lemma, where if you take the k-step of any walk, you can expand it in this way. By definition, there exists some good pair b prime a prime, such that if you look at the s step, it'll be n, and then also again, it can be expanded in this way. So there definitely exists positive a prime and b prime satisfying this first condition, but they may not satisfy this condition. In particular, b may be too large. But to remedy that, it's pretty easy. We can just subtract away from b prime however many multiples of the s minus first Fibonacci numbers that we need to get it in the right range. And now we can look at this new pair, BA, which is exactly this new number here, b prime minus some of the multiples, and then also a prime plus corresponding multiples of the s minus second Fibonacci numbers. And because b prime a prime is good, let me just go back. B prime a prime is good now, so every other, you're now a good pair if and only if you're related in this way, which B and A are. So now BA must be an n-good pair. Because BA is an n-good pair, by the first lemma we had, A can be at most B, and also B is at most the s minus first Fibonacci number just by construction. We made sure that it was a number such that it lied in this range. So this proves that these integers exist, and it's not too hard to go and prove that they're unique as well. And let me briefly also comment on the many names that appear up here. So seemingly slow Fibonacci walks are a fairly natural question to ask because as far as I know, it's been asked at least 3 times independently and then answered in various forms independently by these 3 groups and a couple other smaller results by some other people. And a lot of this theorem appears in earlier work of Englund, Brickell, Johnson, and Jones and Kiss. This is the form that we use here. And the other comment to make is that, okay, this is a fine statement to make, but it doesn't seem to be useful offhand, telling us about the structure of these slow Fibonacci walks. But it actually turns out that almost everything that we know how to say, or even questions to ask about these, can be extracted from this theorem, as we'll see in a moment. Right. So yeah, let's look at some quick applications of this result. So one of the first questions you might ask yourself is how many slow walks can we have for a given number n? We saw for 40 that there were 2 n good pairs, but in general, could there be a million? Could there be a billion? But it turns out that in fact you can have at most 2 n good pairs. So 40 was extremal in this sense. And moreover, for n greater than 1, for n equals 1, there's infinitely many. But for most n, there's only at most 2. And moreover, you can even tell you exactly when there's 2, when this a of n from the characterization theorem back here, when this an is large, is precisely when we have 2 slow walks. So the proof is to take a and b as in the previous theorem. And we know from a couple lemmas ago that all the n good pairs can be related from B and A by this linear combination of Fibonacci numbers. And because B is at most the s minus first Fibonacci number, this k has to be non-negative. Otherwise, this term will be non-positive. And similarly, because A is at most the s minus first Fibonacci number, which turns out to be at most the s minus second Fibonacci number times 2, k can be at most 1 without this being non-positive. So in other words, the only cases that work here are k equals 0, which just gives back the AB that we already knew, and maybe k equals 1. But the k equals 1 case only works when this number is positive. In other words, when a of n is strictly larger than the s minus second Fibonacci. So very quickly from this characterization theorem, we can get this result here that there's at most 2 slow walks, which is far from apparent at the start of the problem. And okay, so one question you might ask yourself is, okay, every n besides 1 has either 1 or 2 slow walks. What percentage of numbers have 2 slow walks? And to aid with that, we define this density function, which takes a number n, counts how many m less than or equal to n have 2 slow walks, and then divides by n to get roughly the probability. And you can go and get a formula for this, and it's very complicated looking. So we'll ignore this for the moment and just go to the pretty pictures. So what we have here is what would happen if you just go to a computer and literally compute this density function t of n around 40,000 to 80,000. It's this weird like sine-like curve. And if you plug in the formula I had back there, what you get is this thing here, which seems to be pretty close to what actually the data is doing. So hopefully you believe me that theorem is correct, even if you don't understand what's going on. There's a couple of things to note here. The first thing is roughly 6 to 7% of numbers seem to have 2 slow walks. But the other jarring thing is that the exact value oscillates with n. There's no nice limiting number that this converges to, as you often would expect in these kind of problems. But this is actually a very common phenomenon in these slow Fibonacci things, where the exact value oscillates with n, and specifically how you can represent n as the power of a golden ratio. We're not going to delve too deeply into the exact specifics. I just want to show that you can get an exact result, and it does match up the picture correctly. But I do want to briefly sketch the proof of how you can prove this, in particular how to use the characterization theorem to do this. So the idea is, instead of directly counting the m at most n, which have 2 good pairs, instead we'll count the triples, s of m, a of m, b of m, corresponding to m, which have 2 good pairs. And the point is that by the characterization theorem, these m are in bijection with these triples. So counting this will be equivalent to counting this, and it'll turn out to be much more obvious to count these guys. So in particular, what are these triples? So first of all, the triples satisfy that if you take this certain linear combination of Fibonacci numbers, you get back your number m, and this number is at most n. So in total, this equation in A and B is at most n. Also from the characterization theorem, we know that B is at most the s minus first Fibonacci number, and A is at most B. And now from the characterization theorem, for just a general pair, all we know is that A is at least 1. But we also know that M is special. It has 2 n good pairs. So if we go back a few slides, that happens if and only if A is large. So we also need this condition on A. So these are exactly the triples satisfying the result. And now this is a lot easier to do computations on. So very briefly, if S is very small, if S is like 5 here, and n is 1,000,000, then this condition here will always be trivially satisfied. So you just have to count B and A satisfying this, which is easy to do. And more specifically, if S is such that n is larger than the golden ratio to the 2s minus 1, we get this very easy regime where we just count everything. Similarly, if S is very large compared to n, none of these triples work. You can just ignore all of these. And this will happen when S is large enough so that the golden ratio to the 2s minus 2 is larger than n. So you can see that there's a very narrow range where this isn't super easy. It's very easy to do for most S. But for n in between these two values, it gets pretty complicated, which is also why the exact theorem statement is complicated, but it is doable. You can sit and do that. Do we have a question from the audience? Okay, let me check the chat. Yes. So not yes. So the answer is yes, in principle. Let me think. So I believe Let me think.
And first, let me just say what the question is, partially for the recording. I don't think it
Yes,
gets the
good
chat.
point.
So the question is, can you describe asymptotically the local minima and maxima of Tn?
Yes, so yeah, good question. So the answer is yes. It is implicit here. If you take the max and minimum here, specifically, I think, let me think for a moment. I think if you take like C equals 1 here, that will be the maximum. The answer is I don't know offhand, but it is, you can do it. You can read through this and pull it off, but I cannot do it on the fly. But that is a good question. And it is roughly between 7.5 and 4.5. That's a good question. Any other questions people have at the moment? Cool. But yeah, that's a good question. But yeah, so that's the idea of how you compute these density results. Right. So from now on, there can be 2 slow walks, as I mentioned before. From now on, whenever I write some walk without any clarification, I'm going to assume it's this kind of canonical walk that we have here with the special B and A from the characterization. So kind of answering Richard's original question about what happens in the next step, it turns out that if we take this canonical thing and we look at the next step, either will be the golden ratio times n floor when s is odd, or the golden ratio times n ceiling if s is even. And again, this follows fairly quickly from the characterization theorem. So the key idea is this weird observation, which is that if having this number, whatever this is, be the golden ratio n floor, is equivalent to saying that if you take the golden ratio times n minus this number, it is non-negative and strictly less than 1. So that's the equivalence. These two statements are equivalent. And further, because we can write n as the s step of the Fibonacci walk, and then we can use this lemma, which lets us write ws and ws plus 1 in terms of multiples of Fibonacci numbers. And then you can expand Fibonacci numbers in terms of the golden ratio. If you do a bunch of algebra, this statement turns out to be equivalent to this thing here. And this will be non-negative precisely when s is odd. And for a and b in this range, it turns out that they're at strictly less than 1. So in other words, when s is odd, this next step will always be the golden ratio times n floor. And similarly, if s is even, it flips it up over there. So for these slow walks, at least for the canonical one, it will always be within plus or minus 1 of the golden ratio times n. And I'll just briefly say that if you take the second slow Fibonacci walk, it will have its next step will either be the golden ratio n floor minus 1 or golden ratio n ceiling plus 1. So it can be a little farther off from the golden ratio times n, but not too far, and in a very controlled way. So given this result, we know that every integer either rounds down in their next step or rounds up. So we'll let capital D denote the set of integers that round down. We'll call these down integers. And again, we can define this density function and ask, what is the density? And again, you can do some numerics and work out the answer. Again, I won't spend too much time on this exact statement. I just want to briefly mention the proof is nearly the same as before. We just count triples. But now, instead of counting triples with a large, we want to count those where it rounds down, which is exactly the triples where s is odd. So there, again, things are relatively simple to do, except for certain regions of n. And again, you can get some nice pictures. Here's what the data actually shows. Here's what the theorem predicts. And again, the exact value oscillates, but fortunately, it oscillates around 50%, which is what one would hope is the case. And again, the exact max and mins can be read off from the exact formula, but I don't know them offhand. Right. So what I just said before is roughly half of the numbers round up, roughly half the numbers round down. But you could ask, how many numbers in a row can you have that round down? It's conceivable that you could have, again, 100 or 1,000,000 integers that all just happen to round down one after another. So to examine this question, we'll write the elements in D in increasing order as D1, D2, and so on. And now we want to ask, how large of a gap can you have between consecutive integers? So if this number were always 1, that would mean every number is a down integer. If this were unbounded, this would say you can have unboundedly large gaps between down integers. And it turns out these numbers are bounded. It turns out this consecutive difference can only be 1, 2, 3, or 5. So in other words, you can go at most 5 or 6 numbers without seeing a down integer, and you can never go 4 steps for some strange reason that just happens to be the case. And then you can also ask this for larger gaps in the down integers. It turns out here the difference set can be any number between 2 and 10, except for 7 and 9, again, for weird numerical reasons.
I have a question.
Yes.
So you talk about like rounding up versus rounding down.
Mm-hmm.
So one natural thing you could do is you could round up if it's at least 0.5 and round down if it's less than that.
Mm-hmm.
Like that would be like how you'd round in the normal way instead of just taking ceiling or floor. Does that
Right.
come at all close to working? Does that get you better than 50%, or is it going to be?
You mean like compared to like how it does like in actual practice, like versus what you would expect?
Well, I'm just wondering if you round, since instead of just taking ceiling or floor, if you round to the nearest integer, does that give you a better result, or is it
So what do you
the
mean by
same?
better result? So like say I have a number n and say it's golden ratio times n is 100.7. So are you asking whether its Fibonacci walk should round up? So like intuitively it should? Is that what you're saying perhaps?
I think, yeah, maybe I'm a little confused by some of the specifics of stuff because I'm wondering like, because this wasn't, you're taking either the ceiling or the floor. I think my impression of it that maybe it is just that you're trying to round it to the nearest integer and you're seeing which times you round up and which times you round down, in which case my question's kind of meaningless.
Yeah,
But
so
I thought,
let me just go really far back here for a moment. So let's just look at a very concrete example.
Okay.
So for 40 Fibonacci walks, we know this is one of the slow guys. And this is in fact the canonical one. If you compute 40 times the golden ratio, it'll be like 64 point something, I don't know offhand. And then it turns out that it's going to round up when you do the next step here. So it turns out here it is the ceiling function.
Yeah. So I guess my question is the answer that you get, it's 64 point something. Because it rounds up, do you know that that something is bigger than 0.5?
Right. Great question. So yes. Okay. So perhaps to rephrase your question, it will either round up or round down, but does it round the way we expect it to?
Yeah, that's what I was trying to ask.
Perfect. That is the most perfect question you could have asked, because let me just go back to right. So we know it either rounds up or down, and intuitively, the closer the floor of n, floor of 5n to 5n is, the more likely we'd expect it to round down, or maybe it might even round to the nearest integer every time. So you could ask, how often is this not the case? So we'll say that a number n is r paradoxical whenever the golden ratio times n minus where it actually ends up in its step is larger than r. So for example, if we take r to be 0.5, and an n that's 0.5 paradoxical means that when you take the golden ratio times n minus where it actually ends up, either the floor or ceiling, it's not the closest integer to the golden ratio times n. In other words, it doesn't round to where we expect it to. So you can ask, A, does this happen? And B, how often does it happen? Which I think is roughly what you were asking, Alex. Or at least I'll pretend it is, because
Yeah, no, that's pretty much what I was looking for.
yeah,
So
I was like, wow,
great.
this is exactly the question that needs to be asked right now. All right, so again, we can define this density function, PNR. And there's a couple results. So the first one is that there are no numbers that are too paradoxical. In other words, if r is at least 0.72, then there are no such things. So what this says is that if I told you the golden ratio times n were 100.75, then for sure, it has to round up in its next step. There's no way it can jump down that whole 0.75 down to the floor. It has to always round up. But if you're any smaller than this, you can have it round the wrong direction. And specifically, there's these 5 cases depending on n and the exact value of r. That's very complicated. But again, pretty pictures. So what we have here is the data and theory plot for these 0.5 paradoxical guys. So these are the percentage of n which round the way you wouldn't expect them to. And it turns out that these are, in fact, somewhat numerous. There's about roughly 11% of them, depending on where you are with n. And as you increase this r, this like demand for it to be very strange, it drops down quite a bit. So at 0.6 paradoxical, it drops all the way to around 4%. But there are still examples, and even up to 0.7 paradoxical, you can find infinitely many that do this. So it's a very, so it is somewhat unintuitive based on like Richard's first observation or first claim of it always rounding to the nearest integer. In fact, it doesn't do that quite as often as you would expect it to do, which is fairly strange. Right, so that's a lot of the data you can observe, but it helps a lot for a lot of these problems to be able to first see some data and then work out what the theorem should be. So the question is, how do you do this in practice? How do you find these slow walks? And there's a couple different algorithms you can try. So perhaps the first one you try, and certainly the one I first tried, was you can just try every 2 initial values of your sequence that could possibly that give you the slowest walk possible. And this gives you about an n-squared algorithm, which isn't great, but it's fine, it gets the job done. A much faster way to do it is to, instead of trying to pick the first 2 elements of your sequence, is to pick the last 2 elements. In other words, you know that any slow walk goes something, 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 x, n, for some x at most n. And once you know x, you know the term before it was n minus x, and the term before that was n minus 2x, and so on and so forth. So you can uniquely recover what the whole walk was. So now you just have to guess what the second to last term was. There's only n ways you have to do this, and then you can pick the slowest one. So that's a linear time algorithm, roughly, versus this quadratic one, which is much better. But using the characterization theorem, you can actually do it this much faster. You can do a log n time. Namely, we know that the standard slow walk must go yada yada n, and then if we went one more step, it would either go the golden ratio times n floor or the golden ratio times n ceiling. So in other words, we don't have to try all possible reverse walks. We only have to try these 2. So that gives us the whole answer in log n time. And there's a 4th algorithm, which is a little slower than this, which will be relevant in the next section of the talk, but we're going to change gears in a moment, so I just want to pause and see if anyone has any questions on Fibonacci stuff. Okay, cool. So an observation you might make at this point is that besides all the ways the Fibonacci sequence is special, it's not particularly special, at least in terms of what we're doing here. In other words, given any recurrence relation like wk plus 2 equals alpha wk plus 1 plus beta wk, you can define an n slow alpha beta walk, be any sequence which satisfies this recurrence relation, which eventually hits the number n, and which hits it as slowly as possible. And throughout the rest of this talk, we'll assume that alpha and beta are positive integers, which are relatively prime. So to state our results, we'll need some analogs of the tools we had before. In particular, we'll need an analog of the Fibonacci sequence. And it turns out that the right sequence to pick is the sequence that starts 1, alpha, and then follows the rest of the recurrence. And we'll also need to define gamma and lambda to be these weird functions of alpha and beta. But these are just the roots of this characteristic polynomial. And just as a sanity check, if you take alpha equals beta equals 1, this is exactly the Fibonacci sequence. This is gamma is the golden ratio, and lambda is this minus the golden ratio inverse. But the important thing to just remember is that GK is roughly the Fibonacci numbers, and gamma is roughly the golden ratio. So if you went back through what we've talked about so far, and you take beta equals 1, almost all of our proofs generalize to what we had before. And so to take this, we'll define, again, S of n, where really I should be writing S alpha beta of n, but for simplicity, we'll just write like this, be the number of steps it takes in an n slow alpha beta walk. So the theorem in this easy regime, when beta equals 1, is that whenever S of n is greater than 2, in other words, when you have some non-trivial slow walks, then there exists some unique integers a and b such that n is equal to this linear combination of these Fibonacci-like numbers. Okay, a is at most alpha times b, so a little different than before because we didn't notice this alpha before. And then b is at most the s minus first Fibonacci-like number. And moreover, in this case, you can say that the next step in this walk will either be gamma times n floor or gamma times n ceiling, again, depending on whether s is odd. So great. Almost everything we did before carries over exactly like we did before. So that's nice. When beta is not equal to 1, things get a lot stranger. So in this general regime, again, there exists some unique integers a and b such that n is this certain linear combination of things. Okay, we scale by a beta here, but that's not too concerning. Again, b is at most the s minus first Fibonacci-like number. Now, the first weird thing is that a is at most alpha b plus beta minus 1 times the s Fibonacci-like number. And again, this totally didn't show up before because when beta is 1, this just doesn't appear. And the weird technical difficulty that comes out from this is that before, a was bounded roughly by what b was. But now that's no longer the case. Now b can be 1, and a could be as large as, say, the s Fibonacci number, which can be quite large. And that creates a couple technical problems, which we'll see right now. The first is the strangest condition of this theorem, which is that we need a minus alpha b minus any non-negative multiple of the s Fibonacci number not to be a positive multiple of beta. Okay, so that's a mouthful, but why didn't we see this before? Well, it was because before a was at most alpha b, so this number here was never a positive number. So in particular, it was never a positive multiple of beta. So somehow allowing a to be much larger than b makes this hidden condition show up, which is a real thorn in your side when you're trying to count things in a nice way. And another unfortunate consequence of this bound is that you can no longer totally control what the next step is. Now all we can say is that the next step in the walk is close to gamma of n, but it could be as large as roughly beta to the s. And again, when beta equals 1, this says that your next step is within 2 of gamma n, and you can refine the argument in this case to get this case. But we no longer have control over what's going on. And another annoyance with this, besides being inelegant, is that our nice algorithm, which only checks the 2 walks that either end here or here, no longer works here. So this fourth algorithm I mentioned before, there is a log n squared algorithm, and you have to use it, as far as I know, in this general beta case, which is mildly annoying, but you can do it. So while the characterization theorem isn't quite as nice in this full general setting, you can still prove a lot of the same results. So in particular, you can ask how many slow walks can you have in this more general setting. So the first result is that whenever there's, again, S of n is greater than 2, you have at most alpha squared plus 2 beta minus 1 slow walks. And moreover, there always exists some n achieving this value. And again, it's a sanity check. If we take alpha equals beta equals 1, this gives 2. But the annoying thing with this bound is, while correct and tight, there's often only one n achieving this bound. And I'm kind of more interested in the case when there aren't finitely many exceptions. So to get around this, it turns out the right bound is the following, which is that there exists infinitely many n with this weird number of slow walks, and only finitely many exceptions where there are strictly more walks here. So you have these 2 answers for how many walks you can have, which is kind of a different flavor than what was going on in the general setting. And again, you can define the number of n, which have strictly more now than some given number p of walks. And if you're really like numerics, you can go and sit down and try and work out some densities with this, and you get this very terrible expression, which again we'll ignore for the moment. But briefly, I just want to say that when beta equals 1, the proof of this result and also the theorem statement is very simple and clean and basically what we had before. The main complication now is we have to count triples which satisfy this weird divisibility condition of b minus alpha b is not a positive multiple of beta, yada, yada, yada. So the bulk of this proof now is dedicated to dealing with this technical hurdle. You can deal with it, but it is complicated and annoying. But let's turn to the pretty pictures. So what we have here is alpha equals 2, beta equals 1, and let's just focus on this picture for the moment. The dots are the percentage of m less than or equal to n, which have strictly more than one n slow walk. And the shaded line here is what the theorem predicts. So in particular, you'll notice that the theorem doesn't try and predict what the exact result is for all of n. And the reason for this is, if you recall the proof or the proof sketch of the original density result, there were kind of these three regimes where counting was easy, or sorry, there were three regimes, two of which were very easy and one of which was complicated. So what I did for this density formula was I just ignored all n which had this complicated regime and just only did the easy case, which still was very complicated result. But it's only one case, as you'll notice, instead of three cases like before. And in principle, all the methods I developed should work to extend to give you this full curve, but I didn't want to put myself or the referees through that. So I was just satisfied that at least where it does predict things, it predicts things accurately. And this picture here is those with strictly more than 2 walks, here strictly more than 3, and here strictly more than 4. And you can see that it does a pretty good, darn good approximation for when it's valid. Okay. So now we have all these general slow walks, and a question you might ask yourself is, how slow is the slowest slow walk? So in other words, I give you a number n, and I want you to generate this number as slowly as possible. You can pick any two initial values, and you can use any kind of recurrence relation you want to do it, or two-step recurrence relation. So to be precise, we'll define bold S of n to be the length of a longest alpha beta n walk. And we'll define big S of n to be the set of alpha betas, these generating pairs, which correspond to the recurrence giving you a slow walk. And a priori, any pair alpha beta could be a generating pair for some n. In other words, there might be some really weird large n where it's generated most slowly by a 713 walk. In principle, this is possible, but it turns out this isn't the case. It turns out there's only finitely many possibilities for elements of this generating set. Specifically, these are the only pairs that end up showing up. So part one of this theorem says that for n bigger than 1, every n is generated most slowly by some element in here and nothing else. The second statement of this is that this set is sharp. In other words, for every alpha beta, there exists an n which is generated most slowly by one of these kinds of recurrences. And the third statement is that almost every n is generated uniquely in the slowest way possible by the Fibonacci sequence. And this intuitively makes sense amongst all these alpha beta pairs. The Fibonacci numbers grow the slowest, so you might expect that in general they should generate the slowest walk. And as a corollary to this, you find out that the Fibonacci sequence is indeed special. I did lie to you earlier in the talk. Right, so let's briefly talk about how to go about proving this. And in particular, let's focus on this second point, showing that it's sharp. So for each element of this R set, I want to give you an n which is generated most slowly by it. So for example, if you go to 32, it's generated most slowly by 1, 1, and 1, 2. So that deals with these two guys. To deal with 1, 3, 40 is generated most slowly by it, and 1, 1. To go up to 2, 1, you need to go a bit higher to 3,363. And for 1, 4, the smallest example I have is roughly 5 times 10 to the 14th. So this shows that this set here is sharp. But kind of a nagging thing that you might have noticed is that all of these have the Fibonacci sequence in it as well. So you might ask, is this always the case? Or can we find some n where it is generated uniquely in a most slow way by each of these alpha betas? And you can go back to the computer. You can find for 1, 2, it is the case. You can go up to 171 to do it. For 1, 3, you have to go quite a bit higher to 11 million. For 2, 1, you have to go up to 22 million. And for 1, 4, the smallest example I know of is 5 times 10 to the 30. So it is the case that they all are generated uniquely. And again, I say the smallest one I know of. I did not check all 10 to the 30 numbers smaller than this. I chose this number in a clever way, which we can perhaps talk about closer to the end of the topic there. So this shows that this set is generally sharp. So now we need to show that nothing else can do this. And I'll do this in a slightly more general setting. So more generally, given any set of pairs T, we can define the slowest walk amongst all these pairs alpha beta restricted to T. So now if T were every possible pair, this would just be what we had before, but now we could consider only our favorite kinds of pairs and ask how slowly can we generate them. And more generally, you can, and then also the generating set as well. And even in this more general setting, it turns out that there's only finitely many possibilities that you have to consider. And to prove this, the key lemma we'll need, which is also of independent interest, is that for alpha beta, the length of its slowest walk is bounded by roughly log base gamma of n and half log base gamma of n. And this basically just comes about by looking at the extreme cases of the characterization theorem of what it can be. Right, so now to prove this, what we do is we start with some alpha prime beta prime, which grows as slowly as possible amongst all pairs in T. In other words, its gamma function is minimum amongst all of the possible gamma functions here. And we'll let this number be capital gamma. So for example, if T were the set of everything, this would be the golden ratio. It's the slowest growth rate of any of these Fibonacci-like recurrences. And now the point is, if we take any alpha beta in, say we have some alpha beta which generates some n most slowly, we'll let little gamma be its corresponding growth rate. Then by the previous lemma, we know that how long it takes is at most roughly log base gamma of n. And this, by definition of alpha beta being in the slowest generating set, is bold S sub t. And because this is the slowest rate it takes for any sequence to hit n, it's in particular slower than this alpha prime beta prime that we had over here. And again, by the previous lemma, this is at most roughly half log base capital gamma of n, which you can do a little finagling and get this to a quarter of this. And now just looking at these two sides, this says that log base capital gamma of gamma is strictly less than 4. And because these gammas grow monotonically with alpha and beta, there's only finitely many gammas which satisfy this inequality. So if we just take all these alpha betas in T, that'll be our finite set. And if you refine this argument a bit, you'll get exactly that R set I had before for the case when we consider a qual case. And you can refine this argument a bit and ask how often can a given alpha beta appear in a generating set. And to this end, we'll define the set I to be the set of n which are generated most slowly by alpha beta. And again, we'll let capital gamma be the slowest growth rate amongst all pairs in T. And it turns out you can get this bound on the density function as big O of n to the 1 minus c, where c is log base capital gamma of gamma, this thing we had before. And the proof of this is kind of just a refinement of what we did before. And this kind of gives some intuition for those giant examples we had before. Namely, for 1, 4 walks, its c value turns out to be roughly 1.95. So basically, its density function here is at most n to the 0.05. Sorry, wait, is that correct? Yeah, sorry, no, it's at most, sorry, it's n to the negative 0.95, because c is always at least 1. So it's very, very unlikely that you would find a 1-4 walk just sitting out there naturally in the world. In fact, I had some doubts that they would even exist, but by being clever, you can find one of these guys. And as a corollary to this result, it turns out that in general, if there's a unique pair alpha prime beta prime, which is it has the slowest growth rate amongst all t, then almost every n is generated uniquely in the slowest way possible by alpha prime beta prime. And again, in the t equals all possible pairs case, this is the case for the golden ratio, because the Fibonacci sequence is the slowest growing one. Almost every n is generated by this pair. And the point is that for any other alpha beta, there's little o of 1 percentage of guys that it's in. And then you just do kind of a union bound because RT is finite. So we get the density. So that's that. So this result works when there's a unique guy achieving the slowest rate. But what happens when there isn't a unique pair? So a case of this is when you only consider walks that are 1/6 or 2/3. And here, it turns out both grow roughly like 3 to the n. And now the corollary says nothing. And you might ask, what happens? Which is what I did. So I looked at some pictures. Again, there's a lot of words here. But what the picture says, if you look at these black dots, these are the percentage of numbers which are generated most slowly by 2-3 walks. And those are those which are generated strictly slower by 2-3 walks than 1/6 walks. And these blue dots are those generated strictly slower by 1/6 walks than 2-3 walks. So there's some observations one can make that aren't obvious, and I don't know how to prove them, which is that, for one, there exists a positive proportion of numbers which are generated most slowly by either of these, and for some reason, 2-3 walks are slower. So we're going to close the talk by talking about some open problems, and the first one is answering this question of why are 2-3 walks slower than 1/6 walks? I would be happy even for a heuristic reason for this. I'll note this very strange fact, which is that in general, the 2-3 Fibonacci numbers grow much faster than the 1/6 ones. They both grow roughly at 3 to the n, but asymptotically, these values are much larger. So intuitively, these things should be much faster, but for some reason, they aren't in terms of generating numbers. So I don't know why that's true, but it's weird. You could also ask, we have this upper bound of how often a number can appear as a generating number, but I have no idea about lower bounds. For example, do there exist infinitely many n where 1, 2 is a slowest generator? The data seems to suggest this, but I don't know why. And also, in all the examples I've seen, the generating set has either been 1 or 2 elements. And can you have more than that? I don't know, maybe. And so these two might be hard number theoretic questions. I have no idea. But perhaps some more manageable questions are the following. So you can do all this for longer term recurrences. For example, the Fibonacci sequence. What can you say about these slow guys? And another question I was thinking about recently was, what if you try and hit 2 prescribed numbers? So this is well defined because you can always take the sequence which goes n1, n2, but now if you want to hit both of these numbers and hit the last one in the slowest way possible, how do you do that? I have no idea. Can there be multiple ones? I don't know. So there's still a lot to be said here, but I'll stop here. And now
all right, thank you very much. I'll react to the clapping thing. Not sure how that works. So if anyone wants to ask questions, you can unmute yourself and ask questions. If you need to be somewhere, feel free to leave the meeting.
So I just had a question about your data. So what are you mostly using to generate this data?
Yeah, so I mostly use Sage, mainly because that's the first thing I learned how to do. So it's the only thing I learned how to do. but yeah, it's pretty easy to code up once you know what to do.
Is there a sense of like how far you can go out before the code gets really slow?
Yeah, so it depends a lot on a couple of things. So if you look at, I mentioned before, but so we have when beta equals 1, we have this nice log n algorithm because we know the next step in the walk is one of 2 different things. So there you can go pretty far. When beta is larger than 1, you're limited a lot. Like it slows you down. You can still go pretty far, but let's see, like this number here, that took a while. That took a couple hours to test all these things to make sure that they worked correctly. But it is doable. So I guess this is how far you can go, or I could go. And I'll also just comment on this briefly. The reason I knew to look at this thing is this turns out to be just the sum of 2 of these 1-4 Fibonacci numbers. So the intuition is that it just barely reaches the threshold where it's generated by, so if this were the sum of, say, the 70th and 71st Fibonacci number, that means it's just barely generated in 71 steps by this walk. So you might hope that because it just barely makes it, it works. And then this is also nice because you already know how long it takes to generate this thing because you built it. You know what the number looks like in terms of this Fibonacci representation.
Was there any reason why you chose the 1, 6, and 2, 3 in particular? Did you try a bunch and that was the weirdest? Was this kind of the first one you looked at, or what was the inspiration?
So first I thought, oh, there probably can't be more than one. There's probably always a unique one. And then I just played around with numbers and I was like, oh, here's an example where there isn't a unique pair. So yeah, it was basically just the first one that I came up with. And I think maybe the smallest one. But I should probably make more data on other pairs, but I had to stop at some point with generating data.
Is there a clear way from, maybe you said it and you're talking, maybe I missed it. Is there a clear way once you have this 1, 6, 2, 3 to generate other pairs, or is it just sort of a guess and check process?
What do you mean? Repeat that question?
Oh yeah, so the 1, 6, and 2, 3, there's not a unique pair,
right?
I think. Is there a way to take information about that, like sort of counterexample, and generate other counterexamples, or is it just sort of like random?
Yeah, so there was a general formula I had for like why this came out. Like you can play around with things and like try and disprove that there's a unique pair. There is some like general way you can construct infinitely many counterexamples like this. And I think you can get like arbitrarily many as well. You can get like some with 3 and 4. I think I have it written down in my notes somewhere, but offhand I don't remember how to do it. But there is like a method you can use to do this, other than just get a computer to check things. Yeah, I guess actually in particular, I think if you're looking for things that grow like an integer, I think you can find many of that form. I think that was the trick.
All right, well, if there's no more questions, thanks so much. And I'll see people next week. We have another seminar at the same time.
Thanks for having me.
And I'll let me react with a clap again, and then I'll stop my